Hello, everyone. Come on in.
Hi, Professor Younger.
How you doing, Shonda? Sorry.
Good. Hey, I saw that you were grading the homeworks. I got zeros because I turned them into the other one. I just want to remind you we were going to import it over. I'll start doing all my homework now on this one, but I had already started those two assign. I'd finished them already. I didn't want to redo them.
No problem. If you don't see me remembering to do it, remind me again next week, but I should be able to remember it, hopefully.
I will. And I put my labs in. It says late now, but I have put them into the lab section that you created, but I put them back into the D01B section that I'm in. Yeah, and then the same thing happened with the I guess extra credit. I tried to put it in through the other website and then had to put it in. I don't know, but it's in there. And it will just go. I'll see. The test is tomorrow, right? I had forgotten about it till last night.
Yeah, it's tomorrow at 9 a.m. for people that have me for lab.
Yeah. Yeah. And yeah, so I got everything caught up. I did do the test this weekend. I saw the notice that you sent out. I hope my score went in. It says it went in there, so I don't know.
Gotcha.
Okay. And
no problem.
Yeah. Okay. Just yeah, I'll catch up with you. I'll just remind you. I know that you'll import the homework in we talked about. I'll just remind you whenever you get a chance. Okay. Yeah, I hope you're feeling better. Yeah,
Thank you. Appreciate that.
Okay, I'm gonna get the sound muted.
Anybody else have any questions before we get started? We got about 5 minutes, so plenty of time. As I said, anybody has any questions or anything, now's the time to ask. We do have a test.
Okay.
Those of you have lab tonight have your test tonight, so hopefully you're ready for that. Actually, you're supposed to finish the online test, which covers the same material. That was supposed to be finished as well, so you should be really amped up and ready to do well on this test. And I think I made it pretty easy, so hopefully that helped.
How long?
Shonda, you were saying something?
Yes. How long tomorrow do we have for the test at the lab? Is it 2 hours or do we out by 11 a.m.? Because I forgot my car because I've been busy with my dad. My car inspection runs out tomorrow, and I've got to figure out if I'm going to the guy where I take the inspection, it'll pass, but he does it like early in the morning. I don't want to run over late.
The test is supposed to take 75 minutes.
Do we have from 9 to 11 or 9 to 11:50? Or what time are we leaving?
9 till basically, if you start right at 9, then you'll have from 9 till 10:15, or excuse me, 10:15.
Okay, I didn't know if you were staying in the class till 11 if I showed up at 9:30.
Yeah, if you come a little bit late, I could probably accommodate that.
Yeah, that's all I'm saying. If I got there at like 9:30.
Yeah.
Just so okay, yeah, I wouldn't be like walking in at 10 o'clock or anything like that. That's all. Okay.
Yeah, no problem.
Thanks.
Hey, Mr. Younger.
Hey, Logan, how you doing?
Good, how are you?
All right, what's going on?
So, did you get my text about me asking about for the test tomorrow if I would be able to take it at home?
Yes, yeah, and I told you I can't do that. We're doing a different sort of scenario this semester. So the only way I could do that is if you happen to like be sick and had a doctor's note saying that you were not only sick but that you were contagious. I I might relax that on one or two of the other midterms, but not this first one.
Okay, so there's like no exception because it's like $40 for a round trip for me because of the tolls and gas, and that's just I don't know, for something
Yeah.
that could be taken online, it's just a lot. And it's like 4 hours round trip
The
for
only,
me.
yeah, I mean, I feel for you, and I know that's the issue going on with you. Uh, the only way I could really justify it is allow everyone, and then two, I wouldn't be comfortable with it at all unless you manage to find a really big mirror that you could sit behind you so that I can see everything that's on your screen as well as everything your hands are doing while you're taking it. That's the big crux. We've had some issues of late. So that's why I tried to eliminate the complete online with Respondus lockdown browser and Respondus monitor. So if you want to, if you could think you can find find an actual mirror big enough to put behind you while you take it with a lockdown browser, I could possibly make that happen. But then I have to do it for everyone, and of course, everyone would also have to have a good sized mirror.
I mean, like, I do have a big mirror in my room that I could sit in front of, and I could show that in the camera if you would let that happen. Like, it's just a lot of time and money for me to come over there
Yeah,
for
I get you.
a t
I mean, it is part of the point though, was regarding having you at those lab meetings. It's quote unquote not hands-on lab stuff, but it is a hands-on thing where we know exactly, that you are not having access to anything, that no one's in the background or under the table helping you or anything weird like that. So that's the main reason why I'm trying to eliminate that. But yeah, if you can find a camera that, I mean, a mirror that you can set up behind you, I will allow it, but I'll have to make you an entirely different test to do that. And like I said, you have to have it set up where if I'm looking from the camera standpoint of your whatever webcam you have, I should be able to see your computer screen and your hands and under your desk to some extent. And as long as I can see all that, it should be good.
Yeah, that shouldn't be a problem for me. I mean, I'll do everything I can. I
Yeah,
mean,
you
I'll
might
put a
have to
mirror
test it a
behind
little
me.
bit to make sure like when you're on your own webcam, test it and make sure you can see everything you need to see. It's even been suggested that two mirrors have one on this side and one on that side, that kind of thing. I don't I don't want to set up a situation where I'm going to have to start requiring students to buy mirrors, but that's about all we can do. I've had some weird instances of late, and that's pretty much the only reason that I completely got rid of the Respondus monitor as an option. But I can do that for you if you want. And of course, everybody else here has heard that. So that, if that's something you would like to do, you're gonna have to find a mirror and get that done. Uh, sorry. So let me know what you find out or what you find out, and then you can just avoid. You're not here on campus tonight? Oh, that's right. You have lab on Monday, do you, Logan?
I have lab Wednesday mornings.
Wednesday mornings. Oh, so tomorrow morning. Yeah, you can do that tomorrow morning if you'd like. That'd be fine. Just like I said, make sure you get that mirror, and I'll check the camera out. And there might be some problem where I might have to make you take it again or something, or maybe take it on the same day that you come for lab again, something like that. But if the mirror works out, then I'll let it go. I
Okay,
have
thank you
someone
so much.
asking me a question through chat. Let me see what it says. Yeah, yeah. So I guess I just addressed that question, Reynolds, regarding the taking of the test via Respondus lockdown browser and Respondus monitor. That's an option, but you're gonna have to find a mirror. It's not on. I mean, it's not something I can provide for you. It needs to be a big enough mirror where. If you actually connect your webcam and you put the mirror set up the way it's going to be set up during the test, then you should be able to look at your webcam and see all of your computer screen and basically wherever you'd be sitting, it'd be able to need to be able to see your hands or at least the hand closest to the mirror, and then under your desk to some extent.
Question about notes.
Mm-hmm.
I know in the past we've been able to bring our own notes, and I know you provide them on the actual tests themselves. Can we still use our own personal like formulas?
Nope.
I just find it easier for me to reference them.
No, I can't. That's another problem. So the just allowing people to bring in sheets, we'd have to go through and check them and stuff like that. That hasn't been ideal either. Students have been trying to pull stuff, so no, that's why I went ahead and typed up an equation sheet. That is the equations you're actually allowed to take. And that's why I also gave them to you on the practice test, so you'd actually, know what you've got. So now the only thing you can bring with you is a blank piece of paper or blank pieces of paper and a scientific calculator, which you must have. It can't be on your phone or your iPad or anything like that. And then, of course, something to write with. I'm answering Reynolds' question. Uh, It all depends, Reynolds, on that. Basically, I'd have to actually see what it turned out to be, which is sort of the same thing I told Logan. If you take it this way with the mirror, and then I go back and look at the video, and I see any glaring holes in ways that someone could try to cheat, then yeah, I might have to make you take it again. A different test, of course, make you take it again at a testing center or with me monitoring it. So that's the downside. You have to print the equation sheet. Okay, Kara, you must have missed what I just said. Uh, you're not allowed an equation sheet this semester. I've got the equations made up. They're put in the actual test along with the inside covers of the textbook and the periodic table. And 241 equations as well as 242 equations are all included. And actually, the way the 242 equations are put in there, it's 242 chapters 17, 18, and 19, even though 19 is not being tested. No problem. Anybody else have questions? All right, it's time to get cracking now. So as I just round up and tell you guys what we basically were just discussing. So if someone has a desire to take it online in the comfort of their home or somewhere else where they have good reliable internet service and that sort of thing and aren't going to have disruptions, I can let that, but it's going to have to be with you getting a mirror so that I can see uh, not only your face, which is what the respondent's monitor gives me, your face. I need to see your actual computer screen, and what could possibly be on your desk, in front of your desk, and under your desk, that sort of thing. And ideally, see your hands. So I will allow you to do that, but you're going to have to get your own mirror. You'll have to set it up. You'll have to test it yourself. And then if I go online and look at the video and find that it's insufficient, then I will make you take it again. That's the downside of taking a chance with this. So I would definitely recommend you just taking it like you're supposed to at campus, on campus. But I will allow that for anybody. But like I said, there is a chance where you're going to have to take it again, a different version. I'm not going to give you the same test twice, obviously, but it'd be a different version, and you'd have to take it either like at a testing center, or possibly, if I have the time, I might be able to proctor it for you, or find someone else to. Okay, so that's what you can do regarding those tests. Those of you who have lab tonight, you're supposed to have the actual test tonight. Miss Maraskovic knows about it already. In fact, she just sent me a text. Let me check what that is. Hold on, let me respond to this real quick. Uh, All right, that's it. Okay, so I've gotten basically everything. I did have some students that evidently. Uh, One thing I need to remind you about: if y'all have a accommodations report, we generically get them at the beginning of the semester for students that have them. But the rule is you're supposed to, let your instructor know 48 hours in advance, that sort of thing. Uh, I have received some for people that had learning accommodations, and that's fine. But no one specifically had told me they wanted those, so I didn't take any action. That means if you have to have a testing center test, then you'll have to wait till tomorrow. You have to let me know immediately. I'll set it up for you to take it at the testing center tomorrow, and I'll give you a little gap because I don't know what their hours are or how quickly they can accommodate you, but I can give you the test, allow you to take it either tomorrow or the next day. That's your time frame within their hours at the testing center at any of the campuses, and you'll have to, of course, reach out to the testing center to find out what their rules are. They often have rules like you got to bring a photo ID. If you're allowed 75 minutes, for instance, for the test, and they won't let you start maybe for 75 plus 30 minutes before their hours are over, stuff like that. So that's all stuff you got to work out with them. They made it an appointment. That's stuff you got to work out with them as well. So other than that, you take your test tonight. All right. It looks like I had two. I know I spoke to one of my students about it yesterday when I was back on campus. So we'll deal with that. Anybody else have any questions before we get cracking? All right, I'm going to go ahead and open up my good notes so that you guys can follow what's going on. And we're going to start by solving some form of problems from chapter 18 or excuse me, chapter 19, and maybe getting a little further along than that. As I remind you guys, I want to remind you that the test that's supposed to be tonight is only chapter 17 and 18. And if you did what you were supposed to, which is to hopefully have already taken the practice or already have taken the online test, you should be in a really good spot to take it right now. I've got like several emails in the last couple hours, people trying to get out of taking it tonight. All of a sudden people are sick, but they didn't know until after I sent an email, stuff like that. So it's becoming a bit of a problem. If you're going to do that, then you're going to have to provide me with a medical excuse, documentation of your problem, uh, and that's about all we can do. So let's start by sharing my screen. So here we go, share screen. Oh my gosh, people are texting me left and right. Okay, so what I have here is a problem. You should recognize it, of course. It says that an ideal gas is slowly compressed at constant pressure of 2 atmospheres from 10 liters to 2 liters. This process is represented in figure 1913 as a path from B to D. In this process, some heat flows out of the gas and the temperature drops. Heat is then added to the gas, holding the volume constant, and the pressure and temperature are allowed to rise, line DA, until the temperature reaches its original value, TA equals TB. Calculate A, the total work done by the gas in the process, BD to A, and B, the total heat flow into the gas. Okay, so we're trying to first off calculate in part A the actual work done in going from B to D to A. Hopefully you recognize that since work is equal to the integral of PDV, the isovolumetric portion, which is also called isochoric, that particular process means no volume change whatsoever. And without a volume change, you can't do any work. So that part's not going to have work at all. In fact, the only part that has work is the part from from B to D. B is in boy to D is in dog. So let's work with the solution. So what we know is pressure at B is supposed to be 2.0 atmospheres. We know the volume at B is equal to 10.0 liters. We know the volume at D is supposed to be 2.0 liters. And the pressure at D is also supposed to be 2.0 atmospheres. So the pressure doesn't change right there. And of course, that's marked by the isobaric process. And let me see. T is going to change. So TB, which is also equal to TA, does not equal TD. Okay, we don't necessarily know what TD is, but we know it's not equal to the TB or the TA. So what I need to do is calculate the work done. And for part A, work from B to D is equal to the integral of PdV. And then the work done from D to A is equal to 0 because delta V is equal to 0. All right. Now, we were lucky that B to D meant that the pressure or the work done was at constant pressure. So I can go ahead and write 2.0, 2.0 atmospheres for the pressure times the integral of dV. So the work from B to D is going to be 2.0 ATM and times 1 ATM is equal to 1.01 times 10 to the 5th Pascal. And that's because if I kept it in units of ATMs, the units wouldn't come out to be joules or calories for that matter. So we can't do that. The integral of dV, of course, is just delta V. So in this case, we're going to have the final volume minus the initial volume. And the final volume, of course, is only 2.0 liters minus 10.0 liters. And then that can't be in liters either. So I have to say 1,000 liters is equal to 1 cubic meter. And that should actually convert all the units to, notice the ATM will cancel out with the ATM and you got pascals. So pascals is newtons per square meter. And then the liters are canceled out with the liters, and that leaves you meters cubed. So newtons per square meter times meters cubed is newtons meters, which is a joule. So we're good on that one. So I'm going to say 2 times 1.01 e to the 5th times 2 minus 10 is -8. So times -8. And then I'm going to divide that by 1,000. And that gives me -1,616 joules. And notice I underlined the last 2 digits, showing you that those are not significant digits. We're really only supposed to call this negative. Oh, sorry. -1.6 times 10 to the 3rd joules. Now, the fact that it's negative means that work was actually done on the system as opposed to done by the system. So I'll go ahead and circle that. So that's part A. And then part B, they want to know the total heat flow into the gas. Well, if you go from, actually, let me change that to blue again. So for part B, they want to know Q from B to D to A like that. But notice, I'll say equals question mark, but TB is equal to TA. Therefore, delta E internal is just equal to 0 from B to A. Does everybody remember why that's so? We're treating it as an ideal gas. It explicitly said it's an ideal gas, which obviously means that it doesn't really mean that ideal gases exist. It just means that ideal gases are very close to the way reality behaves in certain circumstances, and we're assuming that's what's going on here. But the internal energy for a monatomic ideal gas is 3/2 nRT. So if the temperature doesn't change, then the internal energy doesn't change. So what that tells us is from the first law of thermodynamics, delta E internal is equal to Q minus W. So delta E internal equals 0 means Q is equal to W. So the actual heat is negative 1.616, 2 extra sig figs times 10 to the third joules. Anybody have any questions on that? All right, so that's how that one's done. Everybody think they follow that? Does that make sense? I've got the chats up in case anybody that doesn't have a speaker needs to say something or ask something. All right, I skipped a page specifically in case this took more space than I had on there, but I don't really need to skip a page. So I'm just going to jump right to the next problem. It says in an engine, 0.250 moles or 0.25 moles of an ideal monatomic gas in a cylinder expands rapidly and adiabatically against the piston. In the process, the gas drops from 1150 Kelvin to 400 Kelvin. How much work does the gas do? So that's the question we're trying to figure out for this particular one. So it says an engine, I'm going to say solution again. What we know is N is equal to 0.25 moles. Sorry about that miswriting of the moles there. Whoa. Okay, so that's an ideal monatomic gas. We know delta E internal for an ideal monatomic gas is 3/2 N times R times T. We know that the temperature of the gas drops from, so that tells us T1 is equal to 1150 Kelvin and T2 is equal to 400 Kelvin. And we know that it's done adiabatically. So adiabatically implies Q is equal to 0. And that means from the first law, that delta E internal, which is supposed to be Q minus W, becomes delta E internal is just equal to the negative of W. Okay. So when they ask for how much work is done, the answer is the work done is the negative of the change in internal energy, like that. And that's going to be a negative sign. And notice the 3/2, the N and the R do not change. Crap. The 3/2, the N and the R do not change. So all I'm left with is T final, which is T2, minus T initial, which is T1. So when I do that, I get -3/2 times 0.25 moles times 8.314 joules per mole Kelvin, and then times T2 is 400 Kelvin minus 1150 Kelvin. So ultimately, I can say -1.5 times 0.25 times 8.314 times parentheses. Now I'm going to do 400 minus 1150. And that gives me positive 2.338. And that's times 10 to the third joules. And notice we only had 2 sig figs, so technically I have to call that 2.3 times 10 to the third. Now, in this case, it's a positive amount of work, so this means the gas is actually expanding itself and doing work on the environment. Any questions on that one? All right. Does not appear that anyone has any comments on the chat. So I will move on to the next problem then. So the next problem says determine the change in internal energy of 1 liter of water. Obviously, the density of water is 1 kilogram per liter. It's also 1 gram per cubic centimeter. It's also 1,000 kilograms per cubic meter. That's what we're using here. But it says determine the change in internal energy of 1 liter of water, mass equals 1.00 kilograms at 100 degrees Celsius when it is fully boiled from liquid to gas. Okay. So from liquid to gas, which results in 1,671 liters of steam at 100 degrees Celsius. So you notice the temperature doesn't change. It does say assume the process is done at atmospheric pressure. Now that's a way to circumvent using the actual word isovolumetric or isochoric. They said assume the process is done at atmospheric pressure. So that means it is a constant pressure, and that pressure is 1 atmosphere, which is 1.01 times 10 to the 5th pascals. So here's our solution. So first off, I'm going to say 1.00 liters of water implies MH2O is equal to 1.00 kilograms at 100, which I'm going to call 100 decimal point degrees Celsius. That way, there's no ambiguity as to whether it's 3 sig figs or 1. If I put that decimal point there, that forces it to automatically consider the last 0 as a sig fig. And it's going to change to 1,000. It's going to change to 1,671 liters of steam, also at 100 decimal point degrees Celsius. Okay. It's isovolumetric at 1.00 atmosphere. Okay. And what they're asking for is the internal energy. So delta E internal is equal to question mark. Now, the first law of thermodynamics gives us that delta E internal is equal to the heat added to the system, Q, minus the work done by the system, W. Now, no temperature is changing here. The only thing that's happened is we're changing state. And and the changing of state is basically given by a formula M of the water times the latent heat of vaporization. And then the work, since it's isobaric, is minus P times delta V. Okay, obviously the final volume is much bigger than the initial volume, so you can see that delta V is going to be a positive, and therefore it's going to subtract from this. So in order for us to do this, we need to know the specific heat, or excuse me, the latent heat of fusion of water, which I think is 22.5 times 10 to the, no, it's 22.6 times 10 to the fifth. So I'll write 22.6 times 10 to the fifth. That's joules per kilogram. That's the latent heat of vaporization for water, steam, ice, all that good stuff. And then that's times, actually, I should probably, here you go. So I'm going to put that right here. And then I'm going to say, whoa, I'm going to say 1.00 kilograms for the mass of the water. Then I'm going to say minus 1.01 times 10 to the fifth Pascal. That's what 1 atmosphere is. And then the change in pressure is 1,671 liters minus 1 liter. And then, of course, we've got to multiply that by 1,000 liters in the bottom is equal to 1 cubic meter. So it gives us the units that we need. So that's just multiplied by those last two factors. So this one comes 2260000, and obviously none of these are sig figs, and then it's going to be minus 1.01. Notice 1.01 is pretty darn close to 1, so I'm just going to say this is 1,670,000 like that, and these three are sig figs, are not sig figs. So that's how that works. That's 10 to the fifth, and then I've got to take that 1670, which is 1.67 times 10 to the third times 10 to the eighth. That actually already has been canceled out with 1,000 downstairs. So I get approximately this figure, 22.6 minus 1.67. And that gives me 20.93. And obviously you can tell this one, this one, this one, this one, this one are not sig figs. So this is going to be about 20.9 times 10 to the 6 joules is the change in internal energy. Oh, that's times fifth, sorry. Let me fix that. Anybody have any questions on that one? No questions? All right. Well, that's basically the last of the problems that I wanted to do regarding the first law of thermodynamics. Before I go on to the other stuff, what you might notice if you look in your book, from here we go to free expansion, and they just tell you that the internal energy of a gas does not change in a free expansion. And for an ideal gas, delta T equals 0 in free expansion. What do we mean by free expansion? Well, sort of what we just did where we let that steam expand. that's almost a free expansion. If I hadn't had 1 atmosphere of pressure that it had to fight, then it would have been a free expansion. But because it had that 1 atmosphere of pressure, it actually had to do work. So the free expansion would be you have 2 cylinders connected by a pipe with a valve. One of the cylinders has a gas in it. The other cylinder has had its contents completely sucked out as much as it can with a vacuum pump, and then you slowly open up the valve and allow the gas to expand into that other space. That's a free expansion, and that's something that comes in handy from time to time as a construct. So don't worry too much about not knowing why they're telling you that right now. You'll get it later when you get into chapter 20. What we want to talk about now is specific heat, specifically molar specific heat. So what I'm going to do is I'm going to change my pen color and I'm going to draw a line here. And what I want you to do is realize that molar specific heat, whoa. So molar specific heat, which in your book, they're using capital C's, are defined such that the units of CV is equal to the units of CP is equal to joules per mole Celsius degree. So you see the main difference is that it's per mole instead of per kilogram. If you look, so I'm going to tell you here, look at table 19-4, and that'll show you that when you actually switch from specific heat in kilograms, or excuse me, in kilocalories per kilogram Celsius degree to the molar value, you actually get something really neat. So, for instance, if you talk about helium, you see that the lowercase specific heat of helium is 0.75, and that is kcal per calorie or per kilogram per Celsius degree. And CP, again, the lowercase is what we're talking here, is 1.15 kilocalorie per kilogram Celsius degree, whereas neon is 0.148 and 0.246. Now, if we look at capital C, V, and capital CP, which I actually wrote those a little bit too big for their britches. So let me rewrite that. Let's say, well, actually, I'll just do it like this: CV and CP. In this case, we get 2.98. And this, of course, is in calories per mole Celsius degree. And this is calories per mole Celsius degree. And in this case, we get 1.67. But if you look at neon, you get, oops, I copied that wrong. Oh, no, that's good. 2.98, and I copied the 1.67 wrong. Sorry about that. So 2.98 and 4.97. Ah, darn it. And for this, you get 2.98 for neon and 4.97 for neon as well. The neat thing, though, is CP minus CV is equal to 1.99 for both cases. So we're starting to see some stuff. We can also define something called gamma, which is defined to be CP over CV, and we get that that's 1.67 again for these two things. It actually doesn't change too terribly much, but if you look at that table, which I definitely recommend you doing, you'll see that there's a similarity. In this case, I just showed you the monatomic, but then they look at diatomic and you get a similarity between those. In fact, the CP minus CV is still about 1.99 for diatomic. And if you go to triatomic, it's about 2.03 and 2.00. So really, really close to CP minus CV being 1.99. Okay, so that's a big deal, and that's super helpful. If you go to polyatomic, even with C2H6, which I think is sucrose, might be misremembering that, that's only 2.05. So you can see a wonderful thing in using those units for specific gases. We end up getting some nice physical data that tells us they're all very closely related. So what we're going to do now is I'm going to try to make use of the equations that we know of and try to derive a relationship for the molar specific heat. So first off, I want to remind you that the lowercase v means specific heat at constant volume. So CV means molar specific heat at constant volume. Now, something about that, hopefully y'all are already thinking about it, but you might not be. When you actually add heat to a system, according to the first law of thermodynamics, that heat can translate in creating work done by the system or in increasing the internal energy. But if you're holding it at constant volume, then you can't do work. So you get work equals 0, which means every bit of the heat that you put in is going into changing the temperature. Goes to changing the E internal and approximately T. When you do CV or CP, that's the molar specific heat at constant pressure. Delta E internal is equal to Q minus W, and that means the heat can cause work to be done or can raise E internal slash T. Okay, so with that in mind, I hope you realize that CP should be bigger than CV, because in CV, all the energy is going just to do what it's supposed to do, which is raise the temperature. Whereas CP, it's doing multiple things. So you expect CP to be larger. So I can take the equations that we know of, which is Q is equal to, remember we had Q is equal to MC delta T, but with this one, it's going to have to be N times C times delta T. Then it's just a matter of, are we talking about constant volume like that? Or are we talking about at constant pressure, which I didn't want to subscript that. delta T like that, okay? And of course, if you wanted to get that back to the lowercase ones, then that just says that CV is just equal to the molecular weight times lowercase cv, and CP is just equal to the molecular weight times lowercase cp. From periodic table. Okay. Now, if you take the first law of thermodynamics, so from the first law, delta E internal is equal to Q minus W, which for constant V means delta E internal is just equal to N times CV times delta T. Similarly, if you take delta E internal is equal to Q minus W for constant P, then delta E internal is equal to NCP delta T minus P delta V, which we might also write. I'm actually going to write it in a little bit later. I'm going to write that as a D as opposed to delta. Okay. So does everybody follow how I got that? Anybody have any questions on that part? All right. So if I take the heat added at constant pressure, so QP, that's going to be, in fact, looking at that last expression we just did, we can say that it's going to actually be delta E internal, because this part right here, just in case y'all aren't seeing this part right here is the QP. So that's E internal plus, plus P delta V. And then if we take this part right here and plug it in there, then we get QP is equal to QC, which I'm going to call this QC, plus P delta V. And that, of course, means that QP, I don't know why I wrote C there. It's supposed to be QV. Stupid head. I did it twice. And get rid of this one. So ultimately what you get here is QP minus QV is equal to P delta V. Okay. So that might not look too good, but notice we're really close to getting CP minus CV, and that's what we're shooting for. Okay. So I could go back and plug in what QP and QV are. So from this, I could say N CP delta T minus N CV delta T is equal to P times delta P. But P V equals nRT implies P delta V is NR delta T. So in place of delta P, or in place of delta V, excuse me, I'm going to put NR delta T over P. And notice now that these P's cancel out, these N's cancel out, and these delta T's cancel out. So ultimately, I'm just left with CP minus CV is just equal to R. And if you put R, which is 8.314 joules per mole Kelvin, if you put that in the appropriate units, which is calories per mole Kelvin, you're going to say 4,000, or actually you're going to say 1 joule. And you're going to say 1 calorie is 4,186 joules is 1 calorie. And I think that does it. No, actually, sorry about that. Let's erase that conversion factor. Oh, I know, stupid me. It's actually divided by 4.1836. So what I really should do instead of 4,186 is 4.186. And then if you divide 8.314 divided by 4.186, you get 1.99. And that turns out to be calories per mole Kelvin, which is exactly what table 914 gave us. Okay. So this is a really big deal. We've got CP minus CV is equal to R, which is what that table showed us. If we want to go a little further, we know that, for instance, QV, which is the heat when you hold the volume constant, turns out to be just equal to the change in internal energy, which turns out to be, of course, for a monatomic gas, it's a monatomic ideal gas, sorry. It's 3/2 N times R times T, but of course that's also equal to N times CV times delta T. And actually the delta should be in there as well for the T because it's change in internal energy. Darn it. I'm really getting aggravated with that. And that's in CV delta T. So you can now see that this N cancels out with that N, and this delta T cancels out with that delta T. So you're ultimately left with the result, which is partly what we're looking for, is that CV is equal to 3/2 R. Now CP minus CV equals R gives us CP minus 3/2 R is equal to R. That means CP is now equal to 3/2 plus 2/2, which is 5/2 R. Does that make sense to everyone? Now, again, this is not something we necessarily would have thought about you coming up with on your own. That's not really the point. The point is now that you've seen it done, do you understand why it works and that it's okay? And then can you use that? Because this is going to give us some other stuff that comes in super handy. And we've got about, we got plenty of time. We've got about 28 minutes left. So I'm going to go ahead on from here And now we have, for instance, the values of CP and CV theoretically figured out. These are really close to experimental data. Ah, man. So these are very close to experimental results shown in the table. So that's what we call a successful theoretical calculation or a successful derivation. When you actually do that kind of thing with just your basic equations and come up with a result that matches experimental results, then you know that something about your theory is somewhat correct. So that works out pretty well. Your book then goes into the equipartition of energy. And the way I like to explain equipartition of energy is if you imagine that you had, let's say, 1 billion marbles, and then you held those billion marbles over a really big box, and in that box, you had exactly, let's say, 500,000 individual boxes that are all the same size. Okay. If you then drop those billion marbles into those 500,000 boxes, since they're all equally big and equally well positioned in that box, you would expect that every box is going to have basically the same number of balls in it. And that's sort of what's going on with the equipartition theorem. What we learned when I was doing the derivation of the average kinetic energy being 3/2 nRT, what we learned was that 1/2 nRT was the energy given to basically the kinetic energy in the x direction. Remember, we started by only considering particles bouncing off the left wall and got the pressure on the left wall, all in terms of V sub x. But then we made the argument that V sub x should be exactly the same size as V sub y, and that should be exactly the same size as V sub z, because there's no preferred direction in space. And when you do that, then you can say, oh, okay, well, then V would equal the square root of Vx squared plus Vy squared plus Vz squared. But each of those are just Vx squared. So it'd be Vx squared plus Vx squared plus Vx squared, which would be square root of 3 Vx squared, which would be root 3 times Vx. Okay. So what that was basically saying is 1/2 of that KT went to the X direction, 1/2 of that KT went to the Y direction, and 1/2 of that KT went to the Z direction. The equipartition theorem says, yeah, that's true, but it's even bigger than that. The number of degrees of freedom you have for your molecules in a sample, each of those degrees of freedom get exactly the same amount of energy because there's no preferred quote unquote degree of freedom. So the fact that the molecule, if it's a monatomic molecule, that just means it's like a neon atom all by itself. So it can move left, right, it can move in, out, and it can move up, down. In principle, it could rotate about its axis, but that's a very, very small amount of energy. Or rotating about any other axis is a very small amount of energy because the radius of an atom is on the order of 10 to the negative 10th meters. So you don't really get any appreciable change as a result of the atom just rotating about one of its axes. And of course, there's 3 of those. So basically, all the energy is 1/2 kT for left, right, 1/2 kT for in, out, and 1/2 kT for up and down. Now, if you up the ante such that you have a diatomic molecule, then you have an atom and an atom, and you have the ability for that entire molecule to go left and right. That's 1/2 kT. In and out, that's another 1/2 kT. And up, down, that's another 1/2 kT. But you also have the ability of this thing vibrating. That's a 1/2 kx squared. So that's a 4th degree of freedom. You also have the ability to rotate this way. That's a 5th degree of freedom. And you also have the ability to rotate this way. That's a 6th degree of freedom. You have the ability for it to rotate this way, but that's just like the atom rotating on its own axis. That doesn't matter much. So that one doesn't come into play. So for a diatomic molecule, it's looking like you're getting more like 6 degrees of freedom. And according to the equidistant theorem, each one of those is going to have to get a 1/2 kT. And if you go to more complex molecules, it's going to have even more degrees of freedom. And each of those degrees of freedom is going to get a 1/2 kT. And your book took the time to show you that in a nice little graph on figure 1917. So I'll say, I'm just going to tell you, read subsection 19-8-2 equipartition of energy and okay, so we did say that already. And look at figure 19-17. Okay. What you'll see is translational kinetic energy gets you 3/2 R. Rotational kinetic energy gets you 5/2 R. And then vibrational energy gets you up to 7/2 R. And that is for just a diatomic molecule, specifically H2. Okay. So that gives you the idea of it. Now we're going to go from there and make use of some other things. You're going to go ahead and read the section on solids. I'm not going to ask you any specific questions out of that. I might in homework and practice tests, but not in the actual tests. I'm going to jump to the adiabatic expansion now. So now let's say adiabatic expansion. What, darn it. And adiabatic, remember, means basically no heat is allowed to enter or exit the system. That's what adiabatic means. So let's start off with our idea of the first law of thermodynamics. The first law of thermodynamics, and by the way, this is subsection 19-9, I think. Yeah, 19-9. So we start off with a version of the first law of thermodynamics, which says the differential change in internal energy is equal to a small change in heat minus a small change in W. Notice I didn't say the differential. As we said, Q and W are not state variables. But for adiabatic, this is equal to 0. Okay. So because of that, we get just negative d bar W, which equals negative P dV. Now, V is a state variable, so we can actually put a differential there instead of the D with a bar on it, right? We also know that dE internal is actually equal to NCV dt. In other words, getting rid of the delta, we just replace it with a d, and we've got that. So if I put that on this side, in other words, I plug that into there, into the left-hand side, then I get NCV dt plus PdV. In other words, I pulled the negative PdV to the same side, and that gives me 0 there. So everybody see what I did? I pulled the negative PdV to the left-hand side, and it became positive. Now I've got that, right? Well, we can also make use of the fact that PV equals nRT, and we know that P dv plus v dp, that's actually the differential of the left-hand side, and that's also equal to nr dt. So everybody follow what we did there? We did the product rule for the left-hand side, and then we did nRT for the right-hand side, becomes nr dt. So now we've got this little guy right here, which I'll underline, and we can actually make use of that by getting rid of, for instance, let's see, VDP, I got that, that all looks good. Okay, so what I'm going to do is solve this for dt. So this tells me dt is in fact equal to P dv plus V dp over n times r, which I can plug into this one. So when I do that, I get n CV times P dv plus V dp over n r plus P dv is equal to 0. You can see that the n's cancel out there, and we can go ahead and sort of multiply through, get rid of some parentheses, and rearrange a little bit. So I'm going to do that. I'm going to say, now that I've gotten rid of that, I'm going to multiply through by r, and that'll disappear on this side, but I'll actually get it on the dv side. So I multiply through by r, and I get c, oops, meant to write this in blue. I get CVP dv plus CVV dp plus PR dv is equal to 0. All right. Now you might notice that we have two dv's in there, so I'm going to get those together. And when I do that, I see that CV plus R times P dv, that takes care of this term and this term. Now all I have left is plus CV V dp, and that's all equal to 0. I can still simplify a little bit more. I know, for instance, that, let's write this over to the side, CP minus CV is equal to R. So, oops, this is hard to see that that's CV, so I want to make sure that's the case. So you see that CV is actually equal to CP plus R. Or actually, that's not what I want. Actually, let's do it a different way. I'm going to solve for CV. Okay. I can change this, for instance. And what I do is I'd pull the, no, I can't do that way. CV plus R. Okay. Yeah, I'll add CV to both sides. And then that'll give me CP is equal to CV plus R. So now I can put that in the equation, and that'll give me CP P dv plus CV V dp is equal to 0. CP P dv and CV V dp equals 0. And if I want to, I can now divide both sides by CV, and that'll give me my gamma, which is what I pointed at earlier. So dividing both sides by CV gives me CP over CV times PdV plus, in this case, we're going to just have left V dp, and then all that's equal to 0. which I can write also as gamma P dV plus V dP is equal to 0. Now that looks kind of nasty, but it's actually quite easy. If I now take and multiply both sides by 1 over PV, okay, you see what's going to happen. I get basically, I'm on blue, so that's gamma dV over V plus dP over P is equal to 0. That's a differential equation that I can easily solve. I should probably make that differential look a little better. Okay. So when I go to integrate that, it's pretty straightforward. I'll do the integral. Gamma is just a constant. So that's the integral of dV over V plus the integral of dP over P is equal to 0, which is the integral of 0 basically. This side gives you a constant. However, we can use the integration constants and that sort of thing just to get the natural log of P plus the natural log, or excuse me, plus gamma times the natural log of V is equal to a constant. Now, carrying that a little further, we had the natural log of P plus gamma times the natural log of V is equal to a constant. So we can actually realize that this is the same thing. Oh, darn it. We can actually realize that this is the same thing as the natural log of P times V to the gamma is equal to a constant. In other words, I use my logarithm rules, which basically says when you multiply a logarithm by a number, that's the same thing as making it the number the exponent on the argument of the logarithm. So that gave me V to the gamma, and then log P plus log V to the gamma gives me P times V to the gamma. So I can raise both sides to the e power, e to the power of the left side, e to the power of the right side, and then ultimately all that gives me is that P1 V1 to the gamma is equal to P2 V2 to the gamma, which is the equation I've been hinting at for the last couple days. That's another adiabatic, or that's another equation that we can use for adiabatic ideal gases. Adiabatic processes with with ideal gases. Okay, so that's a whole nother expression we can use, and we can use that to figure out whatever the pressure is. Before, you just had to use for an ideal gas. Before this, we had P1 V1 over T1 is equal to P2 V2 over T2, and we still have that. But what that means is you need all the variables except for one, but now you can have two unknowns. Instead of just one. That makes sense to everyone? All right, so next time I will go ahead and finish some of the problems on here. What I thought I would do right now, since we only got about 8 minutes left, I want to talk to you about conduction, convection, and radiation. So let's start off. I'm going to put a line here. Darn it. will work related problems Thursday. Now we're going to go to this, and basically heat can be transferred by conduction. That means two things touching. And we know what happens basically at the molecular level. The individual molecules of each item that's in contact with each other have a certain kinetic energy on average. That kinetic energy is higher for the one with the higher temperature. And because of that higher kinetic energy, the higher kinetic energy molecules will bounce against the lower kinetic energy molecules. And eventually that will cause all of the lower kinetic energy molecules to have a, on average, larger kinetic energy, and it will make all the higher kinetic energy molecules have on average eventually a lower kinetic energy. So ultimately the hotter body will cool down and the colder body will warm up until the kinetic energies of the two sets of molecules are the same, at which case they're in thermal equilibrium. That's how conduction works. And if you want to know mathematically the things that conduction is related to, that's what I'm going to do now, is I'm going to give you some relationship for it. So here's conduction. So the heat delivered per time, so heat transferred by conduction per second. That's what that is. You might imagine that that is, of course, directly proportional to the area. So what do I mean by that? Let's imagine a scenario. Let's take this heat reservoir, and it's red for a reason. Okay. It has a temperature T high, say. And then over here, we have another heat reservoir that has a temperature T cold. And what they have between them is a solid rod of cross-sectional area A and length L. So Q is flowing in this way and out of that way. Well, I think you all would agree that Q over T is directly proportional to that cross-sectional area. Does that seem reasonable to you guys? Yeah, the more you have in contact, the better. That's one of the reasons. I was just watching a Big Bang Theory the other day, and it was an old one where they were in the North Pole and the power went out, and of course they're about to freeze to death. So they evidently all of them, all three of the guys had to strip down naked and lay in one sleeping bag with all their bodies touching against each other. And that's sort of the whole point, is the more surface area you have in contact, then the more heat you can share amongst the three of them. So we automatically reach the conclusion that it's directly proportional to A. Would you also agree that it's inversely proportional to L? Does that make sense? So I would say inversely proportional to L, but I'd also say that it's directly proportional to the change in temperature, which I will say is T hot minus T cold. Does that make sense as well? Well, we could also say it's going to depend on the material and put in another value, call it M or P or alpha or whatever. Or we might just say, I want to make this an equation, and I'm going to make the equation that the constant that makes it an equation take into account the actual material. So ultimately, what we get is Q over T, which you might also interpret as dQ over dt. is equal to some constant A times delta T, the temperature, over L. And this part, of course, is called the temperature gradient. Because it really is the temperature difference over a distance. But that's your convection equation. And it's pretty straightforward to use, as you can tell. And just remember, it has units. For instance, this has units. Q over T of joules per second, something like that. And this quantity right here is the thermal conductivity. Have any of you ever worked construction or at least been like on a construction site where some house was being built and they were putting up insulation and stuff like that? Anybody seen that stage of a house before? Well, that stage of a house is when they're insulating, and you'll notice on the walls of the insulation, it'll say R13 or R11 or R12 or stuff like that. That R is in fact basically K divided by L. So I just wanted to point that out to you. So that is related to the R value that you're used to dealing with in terms of the housing and building industry. But it's in such a way that it's weird. But that's also why R13 is what you use for 2x4 walls, and R19 is what you use for 2x6 walls, because R is basically 1 over K over L. So the fact that a 2x6 wall is thicker tells you that the R19 is a result of the 19, or the 19 is a result of it being a thicker wall. So R is like 1 over K over L, which is like L over K. Okay? So that's one issue. The other issue is with, and I'll solve some problems for this later, but the other issue is with radiation. And with radiation, I'm skipping convection. But with radiation, we have something different. It is called the Stefan-Boltzmann equation. And in that case, we call L the luminosity. That's what we do in astronomy anyways. It's the total amount of energy put out per time. Is also equal to Q over T. That's also equal to dQ over dt in some cases. But in general, that's equal to epsilon sigma surface area times T to the fourth. This is the Stefan-Boltzmann constant. This is the surface area. And this is the temperature. Temp in Kelvin. And this is called the emissivity. EMISSIVITY. 1 for a black body. So your book does that. I'll get into more details with that later, but its time is up, so you guys are free to go. I'll wait for the last person to leave. Everybody that has your test tonight, good luck. I think I made one that's supposed to be pretty easy for you. It didn't take me any time to solve it myself. I didn't make any mistakes this time, which often happens. So that tells me it's also a pretty good, easy little test. Don't get caught cheating. You will need your lockdown browser. If you have your own computer, that'd be helpful, but it's got to use the lockdown browser. And if not, you can use the one in the computers in the lab, and they have lockdown browsers available to them. Good luck, everyone. Anybody else? John, did you have a question, sir? He might be going. I don't see him typing anything, so I guess that's it. Bye, everybody. Bye-bye. Oh, you don't see the mean path thing. That's because I told everybody we're not testing on the mean free path. It was appearing in the practice test and the homeworks, but I'm not putting any of that on the actual tests. Good luck. Kick some butt for me, John.